Okay, so in the last segment, we observed the existence of a free energy functional that has relevance to our problem, at least if viewed as an elasticity problem, right? And then we used that as motivation to talk of, to begin talking of states of equilibria, of the extrema of this free energy functional, and made the observation that, well, we really need to say what it means to take a derivative of a functional, right, of the free energy functional with respect to an entire field, right, which is the displacement field. What we will do in this segment is actually work through that question. Okay, the method we are going to use here is called a variational method. Okay, and the reason it's called a variational method is actually very straightforward. It's simply because we're actually going to consider variations. And the kinds of variations we're going to consider are the following. I'm going to once again draw our field U. That's X, U, 0, L. All right, and let's suppose that this is the field that we have. Okay, this is U. Now, in order to carry out the kind of mathematical operations that we require, we are going to vary this field. And in particular, the way we are going to vary it is this, right? I am going to say that after the variation, the field U looks something like this. Okay, this is the varied field U. And I will also now use yet another color to mark out what we sometimes call the variation. Okay, so the variation that we're talking about here is this, right? We took the field U, varied it as I'm showing you with these blue arrows to get the varied, or sometimes called the perturbed field, right, which shows up in green. Okay, so right now I am going to label the green field here. The green field is what I am going to label as U sub epsilon. Okay, where that subscript epsilon is, it comes from a parameter that I'm going to introduce that we use to sort of control the amount of variation we have here. Okay. Okay, so here are the definitions, right? So what we are doing here is consider a variation okay, that I am going to label W, okay, such that the quote-unquote varied or perturbed field is the following: U sub epsilon, which is now defined as the original field U plus epsilon times W. Okay. Now I've introduced two new quantities here, right? I've introduced W as well as epsilon, right? I need to say something about them. Epsilon is just a number, okay? So epsilon belongs to the real numbers. That is just a number. So if I state this, and as you can imagine now, the W is a variation. I'm calling U sub epsilon the varied field. It implies that W is also a field, right? Right, because U is a field, U sub epsilon is also a field, and clearly, and epsilon is just a real number. Obviously, W has to be a field. That's right. And if you stare at this figure I've drawn here, the graph, what you should be able to see is that I'll switch colors here. The blue arrows essentially represent the field epsilon W, right? So let me try and draw epsilon W here. It varies something like that. It gets a little smaller here, bigger again. Okay, something like that, right? So this is epsilon times W. Okay. Now, now remember, epsilon is a real number, right? What is that telling you about W? Okay. Note, definitely the way I've drawn it at least, W of 0 equals 0. Okay. With all these leading hints, you should now, and given the fact that W itself is a field, it's a field which satisfies W at 0 equals 0, it should tell you something about the space that W belongs to, right? Observe that as drawn, W belongs to the space that we've been denoting as V, right? Which consists of all W such that W at 0 equals 0. Right? Indeed, that's the case. Now, there is a reason, a very strong physical and mathematical reason why W is always chosen to be to vanish at 0. In fact, more importantly, W always vanishes at the Dirichlet boundary. Okay, so W vanishes at okay, and this is a principle, right, in variational methods. In order to see why W vanishes at the Dirichlet boundary, it's useful to recognize that really the field that we care about is U. W, and in fact epsilon as well, are things that we've introduced, objects that we've introduced into the formulation in order to serve our purpose, in order to take us towards where we want to go. Okay. In particular, as you can, given the fact that I've called U epsilon the perturbed field, the varied or the perturbed field, you may imagine that now we're, and the fact is we are going to use it to construct our notion of a derivative. In computing derivatives of our free energy functional, you will appreciate that it is of critical importance that we do not violate the Dirichlet boundary condition, right? Because if we do, we are actually changing the problem. And so it is that W vanishes at the Dirichlet boundary in order that the perturbed field U sub epsilon does not violate the Dirichlet boundary condition. Okay? This is so that U sub epsilon obeys or satisfies the Dirichlet boundary condition. If we were to take a variation, if we were to construct a perturbed field that violated the Dirichlet boundary condition, we would no longer be even talking about the same problem, okay? Because the data of the problem would have been changed. All right, so it is for this reason that W must vanish wherever we have a Dirichlet boundary condition. Okay, of course, by now you are recognizing W as our weighting function, right? What we've called our weighting function in our finite element formulation, or at least in the weak form leading up to our finite element formulation. Indeed, that's correct, and it's no accident that I've labeled this as W as well. Okay, all right, but how does all of this help? Here's how it helps. What we are going to do is consider the perturbed functional consider the perturbed functional pi, but now evaluated with U sub epsilon. Okay, right? It is essentially what we would compute for our free energy functional by using the green curve from the previous slide. Okay, the U sub epsilon curve. All right. Now is where our epsilon comes into the play, comes into the picture, right? All right. So we consider the perturbed functional pi sub epsilon, and in fact consider the following, right? Supposing we take pi sub epsilon, sorry, pi of U sub epsilon, right? Now, the role of epsilon here, if you look at how we used it in constructing U sub epsilon, the role of epsilon is to sort of control the amount of variation we're applying to U. Okay, think about it. Actually, for that, let me just go back to this slide. Think about it. Look at this slide. We've defined what W is, and having defined W, it already gives us a variation. In fact, given that epsilon is just a real number, it should be clear to you that if we change epsilon, that blue curve on this graph will simply get scaled. Okay, it will not fundamentally change its character, right? It will simply get scaled. So really the role of epsilon is to control the amount of variation. W controls the nature of the variation, epsilon controls the amount of the variation. Okay, so what we want to do is, having looked at how the free energy functional changes or gets perturbed with our variation, we've already decided about the shape of the variation by choosing W, right? Or by taking various W's. In order to control the amount of that variation, we are going to look at how the perturbed functional varies with respect to epsilon, right? As we look at its derivative with respect to epsilon, we get a sense of, well, okay, I'm going to add a variation of a certain shape. As I now control the amount of variation, I know how much my functional varies, right? So we want to consider this, all right? So this gives us the amount of variation in pi having the amount of variation in pi for variation in U having chosen, shall we say, the form of the variation. And the form of the variation comes from W. Okay? So already, if you think about it, we're now getting close to this notion of, well, how much is pi changing with variations in our field, U. Okay? Now, however, what we want is a variation in pi right about U. Okay? All right? So if we further consider now dd epsilon of pi u sub epsilon, we construct this derivative with respect to a scalar epsilon, which is easy to do, right? Because one thing you will note is that with respect to epsilon, pi will be a function. Okay? And we'll see this clearly. All right. Maybe I should just state this here. Pi is a simple function of epsilon. Well, it's a functional of u. All right, so let's get back to it. We want to know how pi varies with u, but right around the actual value of u. Well, that can be delivered for us if after computing this derivative of pi with respect to epsilon, we simply set epsilon equals 0. Because after all, epsilon equals 0 makes u sub epsilon the same as u. So here we have it, right? So what this tells us is the derivative, well, let me not straight away call this a derivative. This is the variation in pi with respect to u at u itself, right? For that field. Okay? And this indeed, if you think about it now, this indeed is our notion of the functional derivative. Okay? Because now we've constructed a clear notion of what it means to take a functional and look at how it varies with respect to a function, right, a field. Okay? All right. This is a good point to end this segment as well. When we come back, we will apply this machinery to the particular functional we've created.